Hello everyone. Sorry for the inconvenience. The live lecture didn't quite work out. There was an issue with the power settings on the laptop that changed the video driver somehow, which messed up the screen capturing software. Anyway, I have everything set up now. Yeah, and I hope that the recorded lecture is also going to be fine. I really want to be able to offer live lectures. I think that's important. So next week I'll be back to doing this live. But sadly, this is the way we'll have to do this week. I'll rehearse the notification that I kind of made during the live lecture about the project sessions. So yesterday was the first deadline, or the day before yesterday was the first deadline. And what I noticed is that a couple of you didn't hand in any theory parts. I'd just like to point out that the theory part will be part of the grading, so please make sure that you also submit that for the next homeworks. And I haven't looked at these homeworks at all, but I would still like to stress that it's important that everybody hands in an individual copy, right? So make sure that you have your own code. I don't want to see any code copy-paste. Okay, then for today's lecture we're going to talk about eigenvalues and modal decomposition. So in the last few lectures I kind of laid out some groundwork, some mathematical bases. We talked about function spaces, differential operators as mappings between function spaces. We talked about bilinear forms and linear forms, which take functions and spit out numbers. So these are all kinds of linear mappings on these spaces, and that felt very familiar because that's exactly what we're doing in linear algebra. In linear algebra we're also talking about linear operations on, well, in that case, these vectors. And we found that with this more general notion of linear algebra that also encapsulates these function spaces and differential operators in bilinear forms, we can actually generalize a whole bunch of notions from our linear algebra knowledge also to the field of differential equations and function space in general. So the particular example that we looked at last time was a projection, where we saw that we have an idea of what a projection means for linear algebra, and we could actually generalize that to also work for functions and function spaces. So today I want to continue with that school of thought. And we're going to talk about eigenvalues and eigenfunctions, eigensolutions. And of course we know those from linear algebra as matrix acting on vectors equals a scalar multiplied by that vector. And we also, if we took a partial differential equations class, then we have also seen this a little bit over there. And today we'll see what the connection is, where that's coming from. And specifically we'll also see that this is helpful when we want to construct a reduced order model, because then the eigensolutions and the eigenvalues say something about how important a certain solution is to the potential span of solutions. Yeah? So we're only going to take those that we find particularly important. And towards the end of the lecture I'll show the new assignment. Yeah? So that's going to be about modal decomposition. So it's going to use the theory that we'll discuss about, that I'll discuss today. The first thing I want to do though is kind of make the connection between weak formulations of a partial differential equation and strong forms. So far I've only talked about the weak formulation, and I derived that from energy minimization. So what we did is we took the following energy potential. So we have the energy potential that looked as follows. We have the functional, right? It's taking a function. U is a function. It's defined at every point in our domain. It's a vector valued function. And what it spits out is a number, the energy, and that is computed as the integral of half of the symmetric gradient of U, double contracted with C, the stiffness tensor, double contracted with the symmetric gradient of U again. So that's the internal part. And then we might also have some forcing, so I kind of avoided talking about this earlier because I wanted to have a zero right hand side. But in a more general sense we would also have, for instance, a certain body force everywhere in the domain. It might, for instance, be a gravity. And then its addition to the energy looks as such. and we might have some tractions along the boundary of our domain. And specifically on the northern part of the boundary, that might be Tn also dotted with u, force times the displacement. Yeah. We found that if we now take a functional derivative here, a Guiteau derivative, then we find, okay, so this is now kind of overlapping. Sorry, I'll repeat that. So the last term here is going to be an integral on the boundary, on the northern part of the boundary, and where we have a traction and also displacement. Yeah, like that. And if we take a functional derivative to find the solution, the function that minimizes this potential, then we find a statement that we call the weak formulation that characterizes that solution, and that statement is to find some solution u in H1, 0, D, where D is indicating that this is a vector with D components, where D is the dimension of our problem, might be two-dimensional, three-dimensional. And we define this space as all the functions, so this is the set of all the functions that are in H1, and this one we talked about last time. So these are all functions that have one derivative well defined. And then I added a subscript 0 here, and what that means is that our solution u is going to be equal to 0 on the Dirichlet part of the domain. Yeah? So what our problem really looks like is that we have some domain, and we have planned our solid at some point, and this is what we call our Dirichlet part of the boundary, and that's where we have a displacement of 0. Yeah? That's where we prescribe a 0 displacement. And on other parts you might have a certain traction, and in the center we might have some body force. Yeah? So that's the problem that we're talking about. And what we see now is that our conditions on the Dirichlet part of the boundary, those are enforced strongly in this space. So that's where this 0 comes from. That is enforced directly in all the possible functions that we might consider as candidates. Okay, so we're looking for a function that lives in that space. And we're looking for that function that satisfies, so such that the integral of, well, symmetric gradient of u, symmetric gradient of a test function, that will be equal to the right hand side, it's f times v, plus traction vector dotted with u. Okay, and one of the things that also kind of became important in the first project is the definition of the normal boundary. And the normal boundary, what that really is, it is everything except for the Dirichlet boundary. So even places where we do not specify specifically a traction value, it will still automatically enforce a normal boundary condition there with a traction of 0, right? So whenever we don't specify anything, so when we don't specify a Dirichlet condition, for example, we automatically have a normal condition right there. Okay, and this statement has to hold for all possible test functions v in, well, the same space, h10 d. Okay, now we could identify two parts of this equation. This is what we call a bilinear form, and it's taking a vector u and it's taking a vector v, and I should say a vector valued function, because of course again these are functions, they're defined everywhere on the domain. And the right hand side is what we call a linear form, L of v. Yeah, because if we this behaves linearly in the sense that if we add some other function, it satisfies all the requirements for linearity. And the same thing holds for the bilinear form, which holds for both the U slot and the V slot. So that's why it's bilinear. So the way that we then talk about these operators from a mapping perspective is that the bilinear form is some mapping that takes two functions in H10D, so H10D cross H10D, and it spits out a real number. And similarly, the linear form in mapping terminology is some mapping that takes a function in H10D and produces a number. Now this is the weak form of this problem, and this comes from energy minimization. We also know that the equations of linear elasticity have a strong form associated with them. We can actually derive that from this perspective. So we'll see what that strong form is. Okay. Yes. So the way that we do that is we're going to restrict our test functions to this, the test functions v, which right now are allowed to live in H10. We're going to restrict those to a tighter set, and those are the official space of test functions, which is a space of smooth functions with zero boundary support. So D is what we call the space of test functions which are smooth functions with zero values on the boundary. And well, these are certainly a subset of H10. H10 was supposed to have one derivative. These smooth functions are supposed to have infinitely many derivatives. And H10 is saying that has to be 0 on the Dirichlet boundary. Now these are going to be 0 all around the boundary, so clearly this is a subset and I may choose these functions. Now the second thing that we're going to do is we're going to do integration by parts on the left term, on our bilinear form. And what we end up with when we do that is that we have now a boundary or a volumetric integral minus the divergence of C double contracted with symmetric gradient of U minus F, so I'm already moving the right hand side to the left hand side, and this is weighted by all these possible functions V. And since these are 0 on the boundary, I got rid of my boundary term, so this is simply 0. So this will be 0 for all functions V in this space of test functions, vector value test functions. Now since this is true for all these possible functions, and again there's infinitely many of them, I can choose, for example, a function that kind of looks like this. Yeah? So I can choose these very localized functions, and since this has to hold true for all these possible choices, this is equivalent to saying that the divergence of the stiffness contracted with the symmetric gradient of U is equal to F. Yeah? And this is of course what we know to be our stress tensor. Okay, and this has to be true everywhere in the domain. So that is part 1 of the story. Now we are not quite done yet, because we also have this boundary term over here. So the next thing that we're going to do is we're going to go back to choosing our test functions to be in H10. Now we're going to go back to to V in H10D, which results in, which gives which still gives the integral of minus divergence of C double contracted with symmetric gradient of U minus F V. But now we still have our boundary integral on the Neumann condition, on the Neumann boundary. H10, again the 0 is only specified at the Dirichlet boundary, so we still have now non-zero values on the Neumann part of the boundary, which is adding now this additional term, which is a boundary integral on the Neumann part of the boundary. And this will be Tn minus gradient, symmetric gradient of U dotted with the normal, also weighted by V. Okay, now and from our previous statement we found that this guy was equal to 0. And since this has to be true, but this has to equal 0 for all possible functions V in that space, we hereby can conclude that actually this term also has to be equal to 0. And again, since we can choose all these funny functions that have very local support, that means that this has to be true at every point on the Neumann condition. Yeah? So from the first analysis we had this conclusion, and then in a subsequent step we also can conclude that the symmetric gradient of U dotted with N is equal to Tn. So from this we are retrieving the strong form of the linear elasticity equations. Those are this one, and now we have a Neumann condition as well. And of course, because we define that U has to be in H10, where 0 is specified at the Dirichlet boundary condition, as a third condition, we automatically also have U is equal to 0 on the Dirichlet boundary. So this was on the Neumann boundary. Okay. So what I want to emphasize with this is that we have really two equivalent statements. Yeah? So the statement B, U, V is equal to LV for all possible V in that space is completely equivalent to the partial differential equation where this is specified in the volume, this is specified on a Neumann boundary, and this is specified on the Dirichlet condition. Yeah? So these are two completely equivalent statements, even though they look very, very different. And if we now look a little bit more closely into that, we find that, well, where does the difference really lie? Well, what we have in our bilinear form, so our bilinear form, what was this? Was a mapping that takes a function and another function and gives a scalar. And our strong form, so our differential operator, yeah, this is what we're going to call the differential operator. So the differential operator is a mapping. Well, what kind of mapping is this? Well, it takes a function and the result is, well, the second derivative of this function. Yeah, so it's a mapping that takes a function and gives back a function. So this is a mapping that goes from a function to a function. So even though these are two equivalent statements, the mappings look kind of different. And what I kind of want to say with this is that is really not so different at all, because we're kind of familiar with these sorts of equivalences, again, from linear algebra. So this one I'm going to make the connection with a matrix. So from linear algebra we can make the analogy, and I want to emphasize that's an analogy, the differential operators are not matrices, but we can make an analogy here. And that is that a matrix, it kind of behaves in very much in a similar sense. So firstly, we can interpret a matrix as, well, first of all, we can simply say that a matrix is a mapping that takes a vector and gives a vector. Yeah? So this is a vector to a vector, which kind of relates to that differential operator, to the strong form. But I can also say that I can interpret a matrix to be bilinear. Yeah, right now, if I pre-multiply my matrix also by a vector, a transpose vector, then I see that a matrix can also be interpreted as a vector and a vector to a scalar. And that is the relation with the bilinear form. Yeah, so the equivalence with a weak formulation and a strong formulation is very much the equivalence of a matrix being either a mapping from a vector to a vector or from two vectors to a scalar. And it's the same matrix, it's the same information, but it's a different mapping. Yeah? And in the same sense, a bilinear form and a differential operator, they carry the same information and the same construct. It's just a different approach to the mapping. So this is going to be important for us to understand what eigenvalues are and how we can actually relate eigenvalues for finite element matrices to eigenvalues of differential operators. Okay, so again, this is an analogy, and I should really stress that. I'm not meaning to say here that matrices are differential operators, but of course this analogy becomes very, very close to reality when we're talking about the finite element method. At that point, where our function spaces are finite dimensional and they're spanned by a number of bases, and we can actually produce a matrix from the weak formulation. And then that analogy becomes extremely strong. And also from that perspective, maybe I should also highlight that. So for the finite element method, this analogy becomes very strong. And we can also look at the finite element method then from two perspectives, because what we can say is we can either say, and that's the way we're usually saying this, is that the stiffness matrix multiplied by our vector of coefficients is equal to a force vector. And of course, well, that would in my language right now would correspond to a strong form, but of course that is completely equivalent and saying the same as some vector of test function coefficients times the matrix K times the vector U is equal to the V hat T F for all possible functions, or vectors V hat. So of course these are equivalent statements, and again the first one kind of relates to the weak formulation, and this might be more directly related to some discrete version of the strong equations here. Okay, so is that purely an interesting coincidence, or is that something that we can actually work with? Well, we can bring this analogy pretty far, because what we can do right now is we can take certain things that we know from matrices and see if there is a corresponding idea that is valid for differential operators. Yeah, so what properties that we know from matrices of matrices carry over to weak formulations or differential equations? Okay, now there's a couple of properties that we are very familiar with from matrices. The first one that I might point out is symmetry. Yeah, we talk about symmetric matrices a lot. And the way that we typically say that a matrix is symmetric is that A is equal to A transpose. Now that's not so easily generalizable, because we can say something like this because a matrix consists of a bunch of numbers, and then we can compare all the numbers, and the transpose is literally flipping all those numbers, and then we can see if that's the same. Well, that doesn't translate quite so well into this more general setting, but what we might be able to say though is, how about the mapping? Is the mapping the same? Yeah, so if the mapping that is defined on the left here, is that the same as the mapping defined on the right? Meaning, is this equality satisfied if I map any possible vector in Rn? And if that is the case, well, then these matrices are symmetric. Yeah, the transpose is equal to the matrix. And we can define this independent of having to look at all the different numbers, right? So this is something that works without considering matrix as an array of numbers. Now, is that something that we can generalize to a differential equation now? Well, what I wrote here kind of relates to what I've underlined in green here. Yeah, the mapping from a vector to a vector. So the corresponding form of our differential equation would be the differential operator. So let me now write the differential operator in a slightly more general sense. That's simply an L. Yeah, that's typically the symbol that we use for a differential operator. Yeah, so just to be clear, here in red, that would be L of U. So that's the L I'm referring to. So can we find something that makes sense also for the strong form? Well, I would say maybe not directly yet. So let's try and do this yet in different way. So let's try to look not at the strong form in this matrix language. Let's try to look at the weak form equivalent, and that would be by also pre-multiplying by a vector and seeing if that is equal for all possible vectors xi and zeta. Now the equivalence there with the differential equations would be to say, is B u v equal to B v u? Yeah, and that's something that we can work with. This is something that we can test. We can see if I flip my arguments in the bilinear form, is the result going to be the same? So this is how we would define a symmetric differential operator, to look at the weak formulation and see if this behaves symmetrically. And that kind of gives an answer as well to how we would define whether a differential operator in a strong sense is symmetric. And by itself that might not make sense. Is the Laplace operator symmetric? Well, the answer is yes, because the weak formulation behaves symmetrically. And an advection term, or a first order differential operator, is not symmetric because its bilinear form doesn't behave like that. It's not symmetric. Yeah, so this is sort of a generalization of the notion of symmetry that we're very familiar with from matrices in this functional analysis language. What else can we say about matrices? Well, something that is very important about matrices is whether or not they are positive definite. And this has a whole bunch of important features associated to it. So positive definiteness. So what is the definition of positive definiteness for a matrix? Well, again, there's a bunch of ways of writing this down. I'll immediately write down the version that most closely relates or generalizes. And that would be that if we pre- and post-multiply a matrix by a vector, and I'll already normalize this, so I'll normalize this by the magnitude of those two vectors, squared because I have two of them, and this is now, of course, the norm, the Rn Euclidean norm. Well, if this is larger than or equal to some constant that is positive, so if this is larger than or equal to a positive constant, for each possible choice of vector, then this matrix is defined to be positive definite. Okay, this kind of quite straightforwardly generalizes, and again, I'm pre and post multiplying this matrix, which makes the analogy with the bilinear form. So the idea here is if I substitute the same function v in both slots of my bilinear form, then I define this to be positive definite if this is larger than or equal to, and I'll move the norm now to the right hand side, so c times the norms of v squared. Now what norm am I talking about here? Remember last time we said that every space, every Sobolev space, every Hilbert space, or every Banach space has its own norm associated to it. So on the left I'm talking about the Rn Euclidean norm, because we're talking about these arrows that are composed out of n real numbers. Right now we're talking about functions in H10, so this would be the H10 norm. And we talked about last time what that norm exactly is. And this also has to hold for all possible functions v in H10. And I can either be very picky with specifying everywhere that this should be H10D. This is of course more general than specifically for linear elasticity. The same setup also works for the projects that we're working on. We're talking about Poisson equation instead, so heat equation. So I'm going to stick for H10 for now. Yeah, I don't want to write everywhere, but this might be vector valued. So positive definiteness, we know this for matrices. We can also generalize that to bilinear forms. And in that context, this actually has a new name. This is called coercivity. And coercivity is a very, very important property of a bilinear form, and in that sense a very important property of a differential equation. Because coercivity, just like positive definiteness, says two things about the equation that we're solving, whether that is a linear system of equations or a differential equation. It's pretty much saying the same thing. For a linear system of equations, so when we're talking about matrices, a positive definite matrix is an invertible matrix. So any positive definite matrix can be inverted, which means that I can always solve the system of linear equations. And the same thing holds for a coercive bilinear form. And in that sense also for a coercive differential equation. Yeah, so there's a unique, this property coercivity says something about the existence of a unique solution. Okay, so that's very important. We know that if a differential equation, if the bilinear form of a differential equation, if that is coercive, then a solution exists and it is unique. Now there's something else that coercivity says, just like what positive definiteness says, and it is about the stability of the system of equations, or the differential equation. and that directly relates to the value c. C is sort of a stability coefficient. And I can show that by going over a very simple example. Suppose that we have two systems of equations. A times psi1 is equal to f1, and A psi2 is equal to f2. And suppose that f1 and f2 are not so far apart, so they're pretty similar. Now stability is about, given that f is pretty similar, how much does my solution psi change? Yeah, if my solution psi changes a lot with only a small change in f, then it's a very unstable system. If psi only changes very little with a small change in f, then it's a stable system. So what we're going to do is we're going to subtract these equations, and because they're linear, that works quite nicely, and we end up with the statement that says A times psi1 minus psi2 is equal to f1 minus f2 . I'll have my positive definiteness definition here. Yeah. So this is what we'll define as delta psi, and this will be delta f. Now, if I take this equation and I move these norms to the right hand side, so I'm multiplying both sides by those norms square, then the following statement holds: C times the norm of psi, delta psi right now, square, is smaller than or equal to, because I moved this to the left part of the equality sign, inequality sign, is smaller than or equal to psi t a psi. Yeah, that's the positive definiteness definition. From this equation, we know that that will be equal to psi t times delta f. Yeah, that is our statement. That is this equality. And this was our positive definiteness relation. And this will be smaller than or equal to the norm, the magnitude of psi multiplied by the magnitude of delta f. Yeah? If I take the inner product between two vectors, that will be smaller than the magnitude of the first vector multiplied by the magnitude of the second vector. That's pretty much what that's saying. So now if I look at my leftmost term and my rightmost term, and I divide, sorry, this should everywhere be a delta, 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 and a delta. So I divide by delta psi, the norm of delta psi, and what I see here, and also divide by the coefficient c, and I see that the magnitude of delta psi is going to be smaller than or equal to 1 over c times the magnitude of f, delta f. So this statement is saying that if my delta f is changing a little bit and c is very large, then that means that the magnitude of my solution psi only changes by a little bit. If c is very small, then a small change in f is also going to result in a large change of the psi. Yeah? Delta psi is going to be large. So that's saying something about stability. Yeah? If I have a large c, so this positive definiteness coefficient or the coercivity coefficient is large, then I have a very stable system. If this positive definiteness coefficient is small, close to 0, and our coercivity coefficient c is close to 0, then I have a very unstable system. And for partial differential equations, that means how sensitive is my solution to the right hand side. And what's in the right hand side? Pretty much everything. Yeah? So our force vector is in there, our Neumann data is in there, and even our Dirichlet data can be moved in there. So how sensitive is my solution to any change of my boundary conditions or forcing? Okay, is that important to us? So this also applies here. Yeah? Same thing holds for the coercivity. Is it important to us? Yes, it is. If we're thinking about reduced order modeling, then we're thinking about reducing the size of all possible solution states into a subset. Yeah? Trying to approach that solution space with just a small number of bases. If I have a highly unstable PDE, then my possible solutions are going to fluctuate a lot. Yeah? It's going to be a wide range of possible solution states. Whereas if I have a very stable system of equations with a very large coercivity constant, then our possible solution states are going to be very clustered. And we might be able to be more effective in creating a reduced order model. So this has impact for us, and I think in the next lecture I'll actually specify that very explicitly. So we're going to look at what it's called a manifold of possible solutions, and then we'll see that if my coercivity constant is small, then that has very big jumps from possible solution state to other possible solution state. Okay, so now we've seen the symmetry, which has an analogy for differential equations. We see positive definiteness, which has via coercivity an analogy to differential equations, and we see that that has impact as well for the actual behavior of the system. Is it solvable? Is it stable? Now we're going to move on to the eigenvalue problems. So eigenvalue problems. So what does an eigenvalue problem look like again for a matrix system of equations? What we're saying is we have matrix A, which is acting on a vector psi. We'll add a subscript I because we know we have multiple eigenvalues typically. And we're looking for those vectors such that that operation is equal to a scalar multiplicand of the vector. Now again, what we're doing here is we're acting on a vector to produce a vector. So in the current state, this is something that relates more directly to the strong form of the differential equation, differential operator. Yeah? So we have some differential operator acting on a solution u, a function u, which is simply equal to a scalar multiplicand of the function u. So this is the operation that takes a function and spits out the function. So eigenvalues exist for linear algebra just like they do for differential equations because they fall within that same generalization. It's just about linear mappings acting on vector spaces. And whether those vector spaces are filled with arrows, in the case of linear algebra, or filled with functions, in the case of functional analysis, doesn't matter. This concept of an eigenvalue problem applies in both contexts. Now, what do we know from eigenvalue problems in linear algebra? One of the things we know is that if we're talking about a symmetric positive definite matrix, then each of these eigenvectors, together they form an orthonormal basis. Yeah, so for the case of symmetric positive definite matrices, for a symmetric positive definite matrix, the eigenvectors psi I form an orthonormal basis of Rn. After normalization, of course, because the magnitude of each of these components is trivial, it's arbitrary. Yeah? So after normalization they form an orthonormal basis. So is this something that actually generalizes to this the setting of differential equations? Well, interestingly and surprisingly, yes it does, and this is something that you're actually very familiar with. This is namely exactly the reasoning behind a Fourier series. So this is precisely what a Fourier series is. Because a Fourier series, each of the modes in a Fourier series is an solution to the following differential equation. If we have a ring with the coordinate x, and we're solving a heat equation on this ring, which corresponds to the strong form differential operator that is minus the Laplacian, which in this case is simply minus d squared dx squared, then if I solve this eigenvalue problem, then each of the eigenfunctions is a trigonometric function, a sine or a cosine. Those are exactly the components of a Fourier series. And what that says is that these Fourier series, the components, they form an orthonormal basis because, well, this operator was symmetric according to our earlier definition. We can also show that this is a positive definite according to our previous definition. So each of our eigensolutions, each of the trigonometric functions together form an orthonormal basis of all the possible functions that we're dealing with, and that's exactly what a Fourier series is doing. Yeah, it's representing a function as a sum of basis components, and each of the basis components is a sine or a cosine. Yeah, so I'm just trying to make some connections here with stuff that you're familiar with, hopefully, to make you appreciate the relation between linear algebra and differential equations in this context. So the last thing I'll point out when I'm talking about these eigenvalue problems before I jump into my slides is sort of an energy identity. Because what we have here, if we look at the statement for an eigenvalue problem, well, okay, so this was the strong form equivalent. We can also again talk about the weak form equivalent, and we do that by pre-multiplying the matrix with that eigensolution, the eigenvector. So if I pre-multiply this by psi I transpose, what do I get? I get lambda I, and then the norm, the norm of psi I square, right? That's what I get if I transpose a vector and multiply it with that vector. So what is this statement now saying? Well, this relates to the bilinear form where I'm substituting the same function on both slots. And again, if I'm talking about symmetric positive definite matrices, such as for linear elasticity, such as for the heat equation, then this is actually an energy. So this is half of the energy in that solution, represented by that solution state. So if we look at it from this perspective, what are these eigenvalues really? What we're seeing is that the smallest eigenvalue is that corresponds to that solution U, such that for a given energy, let's say an energy of 1, we have the largest norm or the largest deflection. So the smallest eigenvalue corresponds to the largest deflection for a given energy. So it gives us sort of a physical interpretation of what these eigenvalues actually are. Now what else can we say about from this perspective? Well, actually this is precisely the statement that we had for our positive definiteness. Yeah, that's pretty much this statement, but rewritten a little bit. So the smallest eigenvalue is also a matter of smallest eigenvalue. It's also a measure of the solvability and the stability of the PDE. Well, what can we say about the largest eigenvalue? Well, that's pretty much the inverse of what the first statement was. So the largest eigenvalue corresponds to the smallest deflection for a given energy. Yeah, so these are the modes in the system that require a lot of energy to be forced in their position. So these two statements, the first and the last, they kind of hint towards the use of a reduced order model. Yeah, reduced order model, we might want to take into account precisely the modes that correspond to the smallest eigenvalue, because apparently those are the ones that govern the behavior of the system. And that is precisely what reduced order model is trying to achieve. So this is what we'll do to create a model order reduction. Okay, so let's try and see that in practice. There we go. Okay, so this was the lecture plan that I've talked about for a large part so far. We saw the relation between PDEs and the strong form and the weak forms. I made some connections with the stuff that we know from linear algebra. So we can talk about symmetric operators now, symmetric differential equations. We have an idea of what positive definiteness means, specifically in this case coercivity. So that's about solvability and stability. And now we're generalizing this to the notion of eigenvalues and eigensolutions. We see that the minimal eigenvalues are the ones that are most important. They govern the solvability of the PDE, the stability of the PDE, and they're also the most important modes when it comes to modal order reduction. Yeah, so what I'll show in these slides now is an example of exactly that, and we'll talk about the vibration of a bar. And I'll first do this in the way that we're used to this from an analytical perspective. So how do we solve these equations if we're trying to solve the PDE in a strong sense? And after that, I'll use sort of a discretization of that, and I'll try to generalize that to a modal order reduction strategy. And we'll be able to adopt that strategy for a finite element method, and that's also pretty much what the homework is going to be. Okay, so we have the example here of a bar, and since eigenvalue problems are stated in a strong form, I'll derive the strong form differential equation of this system first. So we have certain displacement field U, and we have a load F, and we have some parameters, the area of the cut, the density of the material, and the stiffness. Okay? And then if I make a single cut through this beam, then I have the body force acting in the center, and I have the normal forces on either side. And if I now want to say something about how this is going to displace, and this is going to be a vibration problem, so this is going to be a dynamic system, then we have that the mass times the acceleration of this block. So the mass and acceleration of this block is going to be, well, the residual of these forces. So we have a normal force that's pointing to the left, the body force is multiplied by dx, dx is this width, and the normal plus the change in the normal force acting towards the right. And we also know that mass times acceleration can be written as, well, the density times the area times dx. So this is the mass, and the acceleration is going to be the second time derivative of the displacement. So then this is some rearranging and dividing by dx. These two cancel, of course. The dx cancels with the f, and I have now a dn over dx. And lastly, the constitutive relation here is that the normal force is going to relate to the displacement as a first derivative with the material stiffness. Yeah? Okay, so the normal force is equal to the area times the stress, and there's the constitutive relation. So if I substitute all of that, then this is in the end the differential equation that I'm trying to solve here on this to describe the vibrational behavior of this bar. Okay. Now, what was our solution approach to solving these types of equations. I don't know how long ago it was that you took a partial differential equations class, but the general idea is that you separate a solution to a partial differential equation in a homogeneous solution and a particular solution. An homogeneous solution is the solution associated to the zero data, zero Dirichlet data, zero Neumann data, and zero forcing. And a particular solution is then one special function that satisfies all these boundary conditions and the force. And eigen problems come into play for the homogeneous part of the solution. Yeah? So that's what I'm going to focus on. So for that particular case, the f here on the bottom right is going to be 0, and a differential equation looks like that instead. Yeah, so that's the differential equation I'm trying to solve. And the solution strategy that we have for this is a strategy that we call the separation of variables. Yeah, so we're going to make the assumption that our solution is going to decompose in a solution in a function in space multiplied by a function in time. And probably I should actually really be saying that it's kind of decomposable as a sum of these separable functions. So that's an assumption. It's an assumption that ends up working. What we can do is substitute this assumed form of u into both sides of our differential equation. And because I'm taking the time derivative on the left, which only acts on the function t, because that's the only function that depends on time, we have now the second derivative of t, well multiplied simply by x, that doesn't change. And on the right we only took the derivative with respect to x, so that only acts on the x part of the solution, whereas the time part becomes doesn't change. So our next step is to divide both sides of the equations by x and t. And what we have then is some part of our equation that is only a function of time. That's the left-hand side, and the right-hand side is only a function of x. So if I have if my left-hand side is a function of t and the right-hand side is an arbitrary function of x, well, how is that possible? Well, that's only possible in the case where both sides are not dependent on t and not dependent on x, but rather are simply a scalar value. Yeah? Because any other solution, if there was some time dependence, well, that could not be equal to some spatial dependence. So what we can do now is we can pull this apart and we can look at only this equation and only the time part of the equation. So then we say that e divided by rho multiplied by the second derivative of x divided by x is equal to minus omega square. And if we multiply by x again, then we get this relation. And we can do the same thing for the time part, and we would get this statement. And these are two eigenvalue problems. Yeah? This is what this is saying is that the second derivative, so the differential operator acting on a function, is equal to a scalar multiplied by that function. And that's the canonical form of an eigenvalue problem. Okay. Now we actually have standard results for these types of eigenvalue problems. In the case of a second order differential operator, we know that these are, well, exactly the Fourier modes, as I talked about earlier. Yeah, so any function t can be written now, that satisfies that relation, can be written as the sum of a sine and a cosine. Yeah, and we know that the frequency associated to the sine and the cosine are precisely that scalar value. And at this point I don't know what that scalar value is yet. I just know that because the left-hand side can only depend on t and the right-hand side can only depend on x, which means that they do on neither, and just know that there has to be some constant value. So what do I do with this now? I have a whole bunch of coefficients. Well, this is where we're going to substitute our boundary data. So that's what we do right here. So these are my possible solution states, or my time function and my space function, where my possible solution state is a multiplicand of those two. And I'm going to look for coefficients that satisfy these boundary conditions. just about fits. Yeah, so based on our first condition, namely that the displacement at 0 is equal to 0, we know that d2 has to be equal to 0. Because my derivative, this is essentially a norming condition, at L, so that's here, which is pretty much saying that the traction is equal to 0. That is a condition of precisely what scalar values omega are permitted. And so apparently I cannot choose an arbitrary value of omega, I'm stuck with having to choose from either one of these sets, where n is in principle ranging all the way to infinity. And so that's where our different eigenvalues are coming from. Then I have at time is equal to 0, I'm setting my velocity equal to 0, that's a choice, which means that c has to be equal to 0. So what do we have so far? We have d2 is equal to 0, c1 is equal to 0. We have an expression for omega. And lastly, what we need for c2 is that we have also an initial condition. Yeah, so we have an initial displacement field, and that's going to describe the motion of the bar afterwards. And if I now plot these functions that I get for x, so these are my possible x states, for the different eigenvalues, then I would get functions that look like this. Yeah, for n is equal to 1, I get this trigonometric function, and as I increase n, I get more and more waves, so high frequencies, more and more waves in the eigensolutions. So just to be clear, because my displacement is always in the length of the bar, this should be looked at as contractions of the bar, right? Even though I'm plotting them being tangential to the bar, they're really in line, parallel to the bar. Okay, so with all this knowledge, I can now substitute everything into my assumed solution for u. So then I end up with this possible sum, right? Because I have all these different potential eigenvalues. So I still have one coefficient left here, and that's going to be based on the Fourier series that defines, that corresponds to the initial condition. Yeah, so those are going to be the remaining c's. Meaning that at t is equal to 0, where this guy, the sine is equal to 0. Am I saying that right? Sorry. Where the cosine is equal to 1. Yeah, okay, so where the cosine, this is going to be equal to 1. Yeah. So we're only left with c times the sine, and from a Fourier expansion, we then know that what the coefficients of c should be. Okay, so how well does this work? Or how does this come into play for a reduced order model, I should say? Well, right now I'm still summing over all these infinite possible Fourier coefficients from all the possible eigenvalues, from all the possible eigensolutions. And we have these infinite sums. Now again, computers, they don't really like infinite sums. So what we could do instead is we could truncate. And again, it's the lowest eigenvalues that are the most important, thus where all the energy of the system is going into. That's also, if we look into the equations right here, then we'll see that those are also the lowest frequency responses, yeah, as opposed to the very rapid responses which dissipate energy immediately. So we're only interested in the lowest eigenvalues which correspond to the lowest number of modes in this infinite sum. So what I might propose to do, as opposed to sum them over infinitely many modes, I could only sum over a couple of modes. So the question is, how well does that work? And I have two examples here. So on the left you see the complete solution, where I'm adding, as an initial condition, I pretty much add a random fluctuation of a whole bunch of Fourier terms, and that's what you see right now. So this is the initial condition. And on the right you see the solution that I would obtain if I did not take into account all the sums, all the infinite series, but only the first, I think, 4. Yeah. So then if we look at the result, then we see that those actually behave quite similar. And again, that is because all the energy goes into those first few modes. Those are the important modes, and those govern the behavior of the system. So can I look at that also quantitatively instead of just qualitatively? What I'm seeing in this graph is the tip deflection. Yeah, so that's the deflection of that guy as a function of time. And then indeed we see that the first, if I just take into account I need the first 4 modes, then the tip of my bar follows the path of the complete solution quite a bit. Certainly if we realize that I truncated literally an infinite amount of terms from the series, right? I'm only taking into account the first 4. And if I'm not happy with this result, I could add a 5th or a 6th, right? That's the idea of reducer and model. Okay, so how does this now function in a finite element context? Yes, I'm going to look at the equivalence with the finite element system of equations. And that equivalence pretty much has to do with the equivalence between strong forms and weak forms. Yeah. Because what I'm going to do is I'm going to assume that the number of basis functions that I'm using for my finite element mesh is so big that the finite element solution in the finite element weak formulation is pretty much exactly the same as the true weak formulation, and thus exactly the same as the strong form of the differential equation. And that's typically what we'll do throughout this course. We're going to assume that our pre-computed solutions, they are so fine that they cover the exact solution pretty well. Yeah? So those are what we call truth solutions. And only afterwards do we try to get a reduced order model from that. So what are we seeing here? Well, this is our weak statement. Here we see our typical Poisson equation. This is the one that we also saw in the first project. And now I still have this time derivative in there as well. And then after that, so this is still the original weak statement. So after that I'm going to substitute my finite element, or I'm going to change the finite element subspace of U. Yeah, so I would use UH instead. And I'm going to assume that every solution is going to be the sum of coefficients times basis functions. Basis functions purely in space, which means that at this point I'm assuming that my coefficients that multiply with these basis functions, that those are functions of time. So each basis function has a time-dependent coefficient associated. So my vector of coefficients is a time-dependent vector, and my vector of basis functions is a space-dependent vector. So if I substitute this assumption or this decomposition into the occurrences in the weak formulation, both for the test function and for the trial function, for u and for v, then we derive our finite element system of equations. And I see this should actually be transposes. Where now we have a stiffness matrix and also a mass matrix. And the time derivatives, because everything else is spatially dependent, they pull out of that and they only act on the solution coefficients. Okay, so this is equivalent to the original weak formulation because we're assuming that n is very, very big, and as we said, weak formulation, strong formulation, they are also equivalent, so this is going to be equivalent to what we see on the right. So let's try and go through the steps of deriving our solution, our Fourier coefficients, our eigenvalue problem that we just performed in the last few slides. Let's try and go through those steps and do the same thing, but now in our finite element representation of the problem. So the first thing that we're doing is we're doing separation of variables, right? We separate our possible solution into an x and a t. So similarly, we want to separate our finite element solution UH in an x and a t. And what that really means is that we are not allowed to fluctuate each mode independently or each basis n independently, but rather we're separating that into one solution vector and one time-dependent function. Yeah? So this is now a solution in space, some vector of coefficient multiplied by the basis functions, and we have separated an associated time-dependent function away from them. Yeah, so this is the equivalence that we have with the earlier analytical approach. So how do we then obtain an eigenvalue problem from that? Well, what did we do in the analytical approach? We substituted this ansatz function into a differential equation. Then that split up very nicely. The differential operators only acted on specific parts of the solution, so that we could separate this into two parts that, well, if the only way that they can be equal for every time and every space position is if they're equal to a constant. So what do we do on the left? We're going to substitute again the same assumption, and we'll find that, well, the time derivatives, they only act on the time part of the solution. The spatial derivatives, they're already actually inside of our stiffness matrix. So this is equivalent to the right-hand side of our original analytical approach. Now we can still divide by each of these parts of the statement. So we're going to divide both sides by t and both sides by v and u. And the only way that these are going to be equal for each possible time is if they are equal to a constant. So now what I can do is, if this guy has to be equal to a constant, then I end up with this eigenvalue problem. Yeah, so that's how we obtain an eigenvalue problem relevant for this physical system. And as you can see, that's very, very similar to the one we have over there. Yeah? So one thing I can point out here is that we still have a minus here. So that minus is kind of hidden in the stiffness matrix, yeah? Because our stiffness matrix, we took integration by parts on the second order differential operator, and that's where the minus kind of got cancelled. Yeah, so the minus is still in there, it's kind of hidden. Okay, yeah, so one of the things that I would kind of like you to appreciate is that the matrices that we're talking about in finite elements, that they have more meaning than simply an array of values, right? They encode information. And in this perspective, they encode, well, the stiffness matrix encodes the Laplacian, the Laplace operator, and the mass matrix encodes that well, this is sort of an L2 inner product. Yeah? So they carry information in them. They're not just arbitrary numbers, they say something about the physical system, just like their eigenvalues will say something about the physical system. And their eigensolution says something about the physical system. And if we use a sufficiently fine mesh, then that will be exactly what the analytical method would say. So let's look at that. So the approach right now is that we would say that UH is the sum over a very, very large number of these hat functions. Those would be our basis functions. So the system of equation that I would solve if I did not use a reduced order model would be an n by n system of equations. And n might be hundreds, thousands, or millions. So what I'll do instead is, going through the steps from the previous slide, we'll solve an eigenvalue system, an eigenvalue problem. And if I solve for the ones associated with the smallest eigenvalue, then I find the most important modes. So what I plotted here are actually the modes that I obtained from getting from using the X function in Matlab on this system of equations. Yeah, so those are precisely the Fourier modes that I plotted earlier, which I derived analytically. So again, this system of equation, even though it's just an array of numbers, it's encoding that analytical physical information. So what I'm going to do next to produce a reduced order model is I'm not going to sum over this very large number of basis functions, but instead I'm going to sum over only 4 of these basis functions, where each of my basis function is no longer one of these hat functions, our standard finite element shape functions, but instead it's going to be one of these modes. Yeah, so I have now a reduced order solution, or a solution associated with a reduced order model, as the sum of coefficients multiplied by eigenmodes. And I can now substitute, as opposed to substituting this, I could now substitute this into the original Greek statement, and I would create a stiffness matrix out of that and a mass matrix out of that, and I would obtain a similar system of equations, but now one that only has 4 by 4 matrices, so that's orders of magnitude cheaper to solve. So what happens if I actually do that, and I'll make, okay, that's what I'm showing right here. So you would create a new mass matrix and a new stiffness matrix, which are only 4x4 matrices. So what happens if I now solve this? And I'll first talk about the graphs that I'm showing here. So on the top left, I have, again, the same graph that I had earlier as well on the top left. So that is the high fidelity, the truth solution. So, or this one I might have actually solved using, I don't know, 1,000 or 10,000 different finite element solutions, or finite element basis functions. The one on the top right is associated to that reduced order model, right? So that's associated to this. So I solved an eigenvalue problem based on the original high fidelity stiffness matrix, mass matrix, and I'm only taking the first few modes. And because I want to show that this is better, this is encoding information from the problem, and this will give us a better solution than simply taking 4 degrees of freedom in a standard finite element mesh, right? The idea is not, for reduced order model, is not to simply use a smaller mesh. We want to use fewer degrees of freedom that carry more information in some way. And we're doing that now by using these modal basis functions, as opposed to 4 linear basis functions. So this graph and this graph, they have the same number of degrees of freedom, but this one has this extra information in it that we obtain from the eigenvalue problem. So what do we get if we let this run? There we go. Well, so far they still kind of look the same, and I think at some point they start to kind of diverge a little bit. And if we again look at the tip deflection, then we see that, okay, so first of all, the exact solution and the high fidelity solution, so that's this guy, well, they completely overlap. You don't even see the exact solution, right? That's the standard assumption that we're making through the construction of our reduced order models. That would be first, have enough computational power that we can use a mesh that's so fine that we're capturing the true physics, or the true solution to the differential equation. Yeah, so those are, they're overlying the lines over there, yeah? Then, if I instead only use the first 4 modes obtained from my eigenvalue problem, then I again get that green line. Well, that's very nicely tracing the true tip deflection. And instead, if I were to very naively simply use 4 linear basis functions, then I get the red line. You see that already starts the diversion. That's only getting worse. So let me again rehearse the point that I also made in the introduction about our objectives for reduced order modeling. First of all, model order reduction is about separating our simulation in 2 phases, an offline phase and an online phase. And during the offline phase, we're happy to do expensive computations. We have time and we want to pre-compute stuff. Yeah? So this is, in the context that I'm talking about right now, this is where we would assemble this huge stiffness matrix, and this is where we would obtain the modal, we do the eigenvalue analysis and we obtain the modal solutions. Yeah? So that's the offline stage. And we're doing all of that such that after that phase, we can go to an online phase, and that's where we can quickly solve new problems, maybe. Yeah? So in this case, time-dependent problems. And at that point, we have reduced this, the size of this, the problem, while taking into account all the information that is hidden, right? That's hidden in that large stiffness matrix. We're grabbing that from the eigenvalue problem, producing only a system of equations that only has 4 degrees of freedom, and that's what we're using during the online stage. And then we can quickly solve the problem. And secondly, also from the introduction, the first lecture, the idea is for model reduction is not to replace any discretization scheme. Again, here we're using a finite element method to first create our eigenvalue problem. Yeah? So we're building on top of the finite element method. And they're also not useful if we're only interested in solving one solution, because solving eigenvalue problems is also very expensive. So it's only useful if instead we want to solve many solutions, for instance, many time steps, right? That's what we're doing here. Okay, so that's sort of my introduction of this first reduced basis method. Reduced basis, again, because we're using only a selected number of smartly chosen bases, and we'll see other reduced basis methods in the coming lectures. Yeah, so this is sort of the first introduction. It has a very physical interpretation to it, because we know what these eigenmodes are. So then, I actually have no idea how long I've been talking right now, but I'll still introduce the project. the new project. So this is a pretty long, extensive text, and that's because I'm giving you a very clear set of steps that you have to go through. But the idea is that we do pretty much exactly the same as what I just showed you in the slides, but then for that two-dimensional example, and not for a vibration problem, but for a heat problem. So the Poisson equation that you used in the previous assignment, that is sort of a stationary heat problem. And then you use certain boundary value, certain boundary conditions on the sides, on the Dirichlet condition, or the Dirichlet boundaries. And the premise right now is that what we're going to do is we're going to certainly, so at that point after you've solved project number 1, you have a certain heat distribution in that object, let's call it a channel, right? This might be something that's going to connect to a heat sink, to a heat source. And we're interested in how that heat changes if we suddenly change the boundary conditions. So what we're going to do is we have now a steady-state heat solution in that domain, and we're suddenly going to connect the left side and the right side to a zero temperature heat sink. Yeah, so the initial condition is going to be the solution that you obtained from the previous project, but then suddenly on the boundary they're going to be zero. So we have zero values on either side of the boundary. So then it becomes a time-dependent problem, a transient problem. And we have here the heat equation that is, that's going to be relevant for us. And what we're going to do is we're going to create a finite element model for that. So this is going to involve having to deal with the time derivatives. I'm going to explain you how to do that. Then we're going to set up an eigenvalue problem in very much the same way as I just showed in the slides. We're going to reduce that by only taking the most important eigenmodes, the eigensolution. That's going to give us new system of equations. Now, what we don't want to do is we don't want to reintegrate the entire basis to create new stiffness matrix and a new mass matrix. That would be very expensive. So in this text I'm also explaining to you how you would use the original high fidelity, very large stiffness matrix, very large mass matrix, plus the eigenvectors to create automatically the small 4x4 matrices. Now then we have to deal with the initial condition in this basis, in this model basis, which kind of relates to the Fourier series in my slides. And then we're going to analyze the solution a little bit. Yeah, so the amount of text is purely to guide you kind of through this. I think after this I'll actually rewrite this a little bit, because I want to separate out the theory questions from this, because this is a combination of theory and practical implementation. So I'll probably factor out the theory questions and compile those as a list on the bottom. But yeah, this is the project, this is the idea what you do. And I'll give you a new version of the Matlab code. And I just jumped to the solution, so I'll probably have to blank that out. So the new project template is, I already included all the code for combining the different squares. So you don't have to continue with the code that you wrote the previous time. I want to make sure that everybody has a code that works properly. So what you're going to get in this code is already something that you can use to compute the stiffness and the mass matrix of the complete channel. Yeah, so after that you'll have to write the code for getting the eigenvalue problem, distilling only the most important modes, creating the reduced order model, and then for analyzing the results. Yeah. Okay, and I think that was it for today. So again, I apologize that the live lecture didn't quite work out. I hope this is still satisfactory for everyone. And next week I hope that everything is going to be set up properly again. Yeah? Okay, see you. Thank you for your attention.